tell you guys what you can do to like ask questions and stuff later. So like anyway, if you have any questions, I know the speaker answer, right? You can go to the H2 chemistry lesson like channel, like it's called H2 chemistry stuff, and just like put your questions in there. If you ask any questions throughout the lesson and you want to answer, you can do that there. You can put your answers there too. But anyway, for today's lesson, it's gonna be about gas laws and energetics. So I've looked through like any of the questions you guys have sent me, and anyway, I'll just do a crash course on like PowerPoint slides first, and then we'll be answering questions on the whiteboard. Is it fine for everyone? Alright, let's begin. So let's talk about today's topic. So this is what we're gonna cover first. It's gonna be quite fast, so like the focus is really on you guys asking me questions. So be sure to like ask me anything that you don't understand later on. So anyway, like let's talk about thermodynamics in chemistry. So thermodynamics are extremely important in chemistry because they basically like govern a lot of the reactions by stability, because like a lot of our reactions are governed by stability. So basically, right, things react because they want to become stable. And it also explains certain observations that we see for gases in real life, and it's super useful from a physics standpoint to like all of your engines and all of the refrigerators and stuff like that. So let's talk about the gas laws. So these are some of the fundamentals for the gas laws. So whenever we do any questions about this topic, right, the following things should be running to everyone. PV equals nRT, like as much as like basic as this is, right, like you really have to think about the ways you can apply the equation to various questions, because even like the most difficult questions in this topic, I'm asking PV equals nRT as something else, for example, and then you need to think about what conditions are being held constant and what conditions are being changed. It's probably like very unlikely for a question to like change every single like value, like for pressure, volume, and temperature. And it's most likely like one of those are most of those are being kept constant, and at most one or two variables is being changed at a time. I also need to think about, is there a need for me to like express the PV equals nRT in terms of another quantity like density or molar mass? And does this gas deviate from or follow the ideal gas conditions? So that's the type of question where you see the curve and all that. And for graph questions, how can you break up the graph in multiple portions and explain them separately? Yeah. So these are types of ideal gas, like your gas law questions. You can just take a quick look and we'll be moving on. Yeah, is that fine? Okay, let's move on. So let's start off with like the gas laws. So basically we know that Avogadro's law just says that the volume is proportional to the amount. Boyle's law says that P equals to constant. Charles' law says that the volume of a gas is proportional to the absolute temperature. And Gay-Lussac's law says that the pressure of a gas is proportional to the absolute temperature. Now, all of these things will mean nothing on words, so what you have to do is derive them yourself using numbers. So for Avogadro's law, for example, right, we know that the starting conditions are that your pressure and your temperature are kept constant. So like, would you guys like to think about how we can derive Avogadro's law using that if we know that our pressure and temperature are kept constant? Like, does anyone want to think of a method that we can use? Then type it in the chat too. If not, I'll just like start like explaining the thing in 5 seconds. Alright, let's do this then. So, let me see. Can you guys see the new screen? Okay. Can you guys see the new screen? Does anyone like just type a yes in the chat? Wait, can you guys not see the screen? Like, can someone just type a yes or something in the chat so that I know that you can? Okay. Can. Okay, let's move on then. So yes, I was going to. Yeah, okay. So let's look at how we can show that Avogadro's law is a thing. So let's say we have two systems, one with a volume of Vx and the number of moles as Nx. Then we have another system with a volume of Vy and the number of moles as Ny. We know that based on the starting conditions that the pressure for these systems is both P and the temperature for both of these systems is T. So like, how can we now prove that Avogadro's law follows the relationship? So let's start by making use of the ideal gas equation. So we know that PVx equals to NXRT. That's our first equation. Alright? And then for our second equation, we relate to this system. So we know that PVy Vy equals to NYRT. Now this is our second equation. Now if we manipulate this, right, we'll see that there's a bunch of common terms. We see that pressure, the ideal gas constant, and temperature are common. So let's express this in terms of those things. So we have it as Vx over Nx equals to RT over P, and we also have it as Vy over Ny equals to RT over P. We know the value of RT over P for both of these cases is the same. So what that means is that it's basically the same as saying that Vx over Nx equals to RT over P, which equals to Vy over Ny. So as a result, we can claim that Vx over Nx equals to Vy over Ny. Do you guys get this? Okay, nice. So like what you guys need to do, right, is to apply the same thing and like try and figure like derive all of like the different like relationships for the other three situations. And doing that basically allows you to like make sure that like remember and understand what's going on at a deeper level. So like just looking at volume as proportional amount doesn't really help you understand because you need to be able to visualize what's going on as well. So yeah. And of course you can try mnemonics, so memorizing this. For example, I remember Avogadro's law is Avocado's law. I don't know why, I just helped me remember it. But yeah, moving on. So molar mass and density. So PV equals to nRT can be manipulated to get you like the equation in terms of molar mass and density, and can be proved to be very useful for certain questions. They ask you to find out the density and molar mass of a substance, or just like give you that information to find something else. So let's try taking 3 minutes to do the derivation now and ask yourself why you can do this. And after 3 minutes, I'll be going through both of the derivations so that and try to explain why that happens. So just take the next 3 minutes to go through this, and we'll begin again at 10:16. Just write it on a piece of paper and stuff. If you guys unsure about how to start, you can send the message to the chat as well. But yeah, or you can just PM me if you're not sure about how to start the derivation. Are you guys ready, or do you need more time? You can just type a 1 in the chat if you're ready, and 2 if you need more time. Okay, anyone else? Like, if you're not sure about what chat I'm referring to, right, if you look at the classroom worksheet, right above it is like a text channel called history, chemistry stuff. And you guys can basically type out any responses you have there. So like once again, if you're ready, just press 1, and if you need more time, you can press 2. Alright, so let's begin like deriving it. So for the most part, right? Okay, let me just switch the screens over first, and there you go. Alright, so let's begin. So we know that in terms of like the only thing that we can really modify in this equation just by looking at it is like, okay, let's just analyze this. We have pressure. Like we haven't really learned how to express pressure in terms of other factors, so we can't really modify this. We also have volume, but it's the same thing applies. You can't really like modify volume in terms of other factors. It's like a condition of the system. And for temperature, we also can't really modify it because like it's also another condition of the system. But for the amount of moles, right, like the number of moles, something interesting happens. We know that the amount of moles, right, can also be expressed in terms of the mass and molar mass of the gas. So we know that N, which is the amount, is equal to your mass over your molar mass. That's really convincing of what it is. So your mass is in terms of grams, and the molar mass is in terms of grams per mole. So if we do grams divided by grams per mole, if we just do like some like dimensional analysis, right, you see that these two will cancel out, then you get 1 over mole minus 1, which equals to mole, which equals to N. So now that we have this, we can basically express the equation in terms of PV equals to M over MRT. So all you need to do to modify like this in terms of molar mass is to bring this over here and bring these two terms over here. So what happens is that you multiply both sides by M, so you get PVM equals to MRT, and then you divide both sides by PV. So that will give you M equals to MRT over PV. So that's the derivation for your basically your molar mass. And there's another way of deriving using this derived density. So we know that density, which is rho, equals to mass over volume. So to modify this, right, all you have to do, right, is once again multiply both sides by capital M, which is a molar mass, so you get this, and you divide both sides by V. So you get PM equals to rho RT, and if you divide both sides by RT, you get rho equals to PM over RT. So that's basically the two basic derivations. Like these are very simple, but they're very fundamental because they help you to like learn whether or not you can manipulate the ideal gas equation. So basically what you look out for when manipulating equations like this is you have to ask yourself, what can you modify in this case? Because not every term can you modify an equation, but some terms can. So you ask yourself, what can I change here? So yeah, that's basically that. And let's move on to the next one, which is back to the slides, and there you go. But if you guys can't see the slides and stuff at any point throughout the lesson, right, you can just let me know. Yeah, if you join, right, can you just like mute yourself first? Just a reminder. Thank you. Alright, let's continue. Okay. So the next part is about sketching graphs using ideal gas equation. So instead of memorizing how the graphs look, right, let's derive the graphs on the spot, and let's think about how we can do that. So like just spend like 1 minute to think about this, and if you guys have an answer, you can type it in the chat, and I'll tell you whether like it's okay if you get it wrong, but I think it's good if you guys just try typing it out. If you guys have an answer, you can type it out, and I'll be going through this very soon anyway. Alright, anyone has a response for like how like we could possibly like derive how to draw a graph on the spot? I guess the general method. You guys can just say it out loud or like type it on the chat. If not, I'll just start in like 10 seconds. Okay, let's begin. So I'll be switching over to the whiteboard now. So once again, if you can't see the whiteboard, just let me know. And yeah. Alright, so let's say we want to draw a graph of P against V. Now this is like a very common graph that they ask you to draw. Now we know that if they ask us to draw a graph against P, like P against V, they're gonna ask us to keep the other things constant. Like in this case, right, that would mean that N, R, T are constants because we can only be changing either of these variables at one time. Like for any graph, right, this is what, like for example, this case is Y and this case is X. In order to have like typical graph like this, you need the other vectors to be constant. You can't have a changing gradient in that sense, like unless like mechanics means. You can't have a gradient that, yeah, you can't really have a changing gradient in that sense. Like the only things that can really be affected are X and Y. So you can have Y against X squared and stuff like that, but you can't, your gradient has to be a constant. If you guys get what I mean. So what actually happens is that we know that PV equals to a constant, and in math and stuff we represent the constant as K. So we can let PV equals to K, and if you just and if you like plot P against V, right? We want P to be on one side, and we want V to be on the other. So we have P equals to K over V. So we're plotting like a graph of like P against V like this. So we know that P is proportional to 1 over V and stuff. So what that means is that the graph, right, if you have to translate this into like Y and X, your Y equals to K over X. And we know that your 1 over X graph for like the positive X-axis will look something like this. So this is what your P and V looks like. Now, if I were to change the temperature in this case, what's actually being changed here is your K. Now, your K is actually still your nRT. So if I change the nRT, let's say increase the temperature, I'll just be moving the entire graph like up. So these are your basically your isotones, as they're called. I'm not drawing them very well, but yeah, so this is like your T1, this is your temperature 2. So that's basically like how you can like derive the graphs on the spot instead of memorizing them. And like I can't stress this enough, right? For chem, you guys want to try and derive as much as you can on the spot and don't rely too much on memory. Like honestly, right, the better you get at chem, right, the less you should have to rely on for memory. Like it's still good to remember things as a backup, but you should feel confident enough to derive them on the spot. So like if you guys are okay with this now, do you want to like derive the rest of the graphs or just move on to the next component of the lesson? Just type 1 for move on to the next part of the lesson and 2 to derive the rest of the graphs. Just type it in the chat. 1 to continue with the lesson and 2 to derive the graphs, like the remaining graphs. Alright, so that's 1. Anyone else? Just quickly just type out 1 or 2. Okay, let's move on. But please do try deriving the graphs on your own time. Anyway, just making use of that. Okay, that's done. And let's have the kinetic theory as applied to the ideal gas. This is basic memorization, but let's go through these anyway. So an ideal gas consists of particles of negligible volume, compatible with the container. Your gases exert negligible attractive forces on one another. Gas particles are in constant random motion. Collisions between the gas particles are perfectly elastic, so they don't lose energy because of collisions. And the average kinetic energy is proportional to the absolute temperature. Now, we know that the first two properties here, right, the one about your particles of negligible volume and negligible attractive forces results in basically like ideal gas behavior. So like based on this, right, can you just type out the two conditions that for like when an ideal gas will be the closest to a real gas? I mean when a real gas will be the closest to ideal gas. There's like two conditions that you need. So if you know, you can just type it in the chat. Just 5 seconds. 5, 4, 3. Alright, then just say out. So like the two required okay, wait, someone's typing now. Yeah, exactly. High temperature and low pressure. Now let's think about why this is the case, right? So we know that your pressure times volume is a constant and your pressure is inversely proportional to volume. So if you have a low pressure, what that means is basically that your gas particles are far apart and there's a high volume. Now because there's a high volume, right, it means that your particles are of negligible volume compared to the one of the container. That's the first thing. And secondly, when you have a high temperature, your gas particles are moving really quickly, and when they're moving really quickly, they're less likely to be affected by the negligible forces of attraction. So think about this way, like let's say you have a constant acceleration rate caused by a force, because your mass is the same, right? If you're moving faster, the acceleration is less likely to slow you down compared to if you're moving slower. So let's say you're moving at 10 meters per second, right? Or 1 meter square per like a 1 meter square per 1 meter per second square deceleration, right, is likely to slow you down more compared to someone who's moving at 100 meters per second. So the same thing applies here. Because our kinetic energy is proportional to our temperature, and we know that when like our temperature increases, our kinetic energy is increasing. as a result, like our velocity increases, your gas particles are less likely to be affected by your attractive forces when your temperature increases. So that's basically like the fundamental understanding behind why these are the two conditions required for ideal gas behavior. So let's move on to the next thing. So like the graph of deviation from ideal gas behavior. So like your deviations, right? If you okay, let me just draw the graph first so you guys know what I'm talking about. Alright, so basically for this thing, you have your PV over RT, which is a constant for molar volume, and you have your P on the axis. So let's say this is the ideal gas line, like it's a straight horizontal line, so it's the ideal gas, and if you have something like N2, it basically behaves like this. So there's like a slight down the middle and it just goes up like this. I'm sure you guys are familiar with this, and let's talk about why this happens, right? So let's say you have moderately low pressure, like this is considered like moderately low pressure, like let's say it's like 200 atm. Over here it's getting closer to 1000 atm. So let's think about for a second like why the pressure like at 200 atm, right, causes like your gas molecules to be have a lower like less than like a negative deviation from ideal gas behavior. So it means your volume, for example, is lower than expected. So the reason why that happens is, right, when your pressure is like relatively low, what goes on is that your gas particles become like relatively close to each other. Like the one is like moderately smaller, right? So gas particles are like relatively closer together. So your intermolecular forces become significant at this point. So your IMF becomes significant. I just on the side said that it's governed by two forces, right? So it's your intermolecular attractive forces and like your intermolecular repulsive forces. So in this case, right, your intermolecular forces dominate, like attractive forces dominate, which causes your gas particles to come closer together than it would be if they were an ideal gas. This causes your volume to be less than we expected, which causes your PV over RT to be less than that of an ideal gas. Now for this region of the graph, as the pressure becomes extremely high, right, your volume becomes very small. So what happens is that your electron clouds start repelling each other, and because of that, your gas particles are pushed far apart and stuff. So this causes your volume to be greater than expected, which causes your PV RT to have a positive deviation. So this is relatively simple in terms of that, right? But the most important thing is like have templates for this, and I'll show you guys a possible one later to like memorize what goes on. So when you have like different gases, right? Let's say that's N2. If you have different gases like H2 or like NH3, let's say it's N2. We know that NH3 has hydrogen bonding and stuff. So like we expect the intermolecular forces to be stronger. What happens is that it goes down more. But we also know that because NH3 only has like 17 electrons compared to N2's like 28, okay, this is more electron cloud basically. We expect this to like deviate less from the ideal gas behavior at higher like pressures. So what you do, right, is for this portion of the graph, we just need to consider like how many electrons does this have, and like how strong will the repulsive forces be, and for this you need to consider the strength of the intermolecular attractive forces. So we have PD, PD, ID, ID, and what's that one? Hydrogen bond. Yeah. All right, let's go back to the screen. Okay, so moving on. Let's talk about like how we can use templates. So it's honestly, right, for Chem, templates are your best friend for quantitative questions, and you guys can sort of like use something like this to like help you memorize. So instead of like writing an novel forward, what you'd like to do is make use of arrows to sort of highlight the links better and to like make the thinking process more clear. So you know that when, for example, a higher pressure is exerted, there's positive deviation because the predominant factor is intermolecular repulsive forces. And because of this, the volume of the system, and because of like the volume of the system become very small, right? Gas particles become very close to each other, and the repulsion between electron clouds, which are intermolecular repulsive forces, cause the volume to be larger than expected or larger than ideal, which causes your PV over RT to be more than 1. Do you guys get that? I just type a 1 in the chat if you guys got the last part, and 2 if you want me to explain again. Does Y stand for yes? Okay, 1. Okay. That's good. Anyone that didn't understand? If not, I'll move on in 5 seconds. 5, 4, 3, 2, 1. Okay, let's go back. Move on. So for a mixture of gases, right? Each gas is a mixture basically like exerts its own independent pressure independent of the other gases. So that's what we call our partial pressure. And we also know that based on Dalton's law of partial pressure, that the total pressure of a system is the sum of the partial pressures in the gases, like in the gas. So I'll be taking okay. I'm gonna do the question now. Okay, let's just do a question now because I think it's important. Let me find the question real quick. I'll be right back. You guys can take a 1 minute break first. Alright, so let's try this question out. So can you guys see the whiteboard? I'm gonna assume you guys can see the whiteboard unless someone says otherwise. So let's just look at this question. So basically what I want you guys to find out for this question, right, is that if I were to open this valve over here and the temperature were kept constant, so your T is a constant, what would be the final pressure of the system? Find the final pressure. So I'll give you guys 4 minutes to do this. Find the final P. So you guys have until like 10:37 to do this, and then we'll start going through this question. So think about everything we have gone through so far and try and solve this. Like the information you have is that your temperature does not change, and your pressure is allowed to equilibrium basically. So yeah, until 10:37, and then we'll go through this again. You guys can type out the 1 if you need more time. Stuff. Actually, if you have the answer to it, you can just send it to me privately or just send it in the chat. You guys can, like, if you guys like don't understand the question, you can also send something to the chat and I'll explain it again. Alright, so someone's already sent me the right answer, so let's begin. So, good job, you actually understood it then, so hopefully that this doesn't help you so far. But let's go through the question anyway, because it's actually like a very like standard question, so let's think about let's before we start writing anything, let's analyze this question first. So like what exactly we're trying to find here? We're trying to find the final pressure. Now we know that T is constant, but that just basically tells us that our number of moles is changing and our V is changing. Because instead of having two individual systems here and here, we're having one larger system with a greater volume and a greater like amount of gas. So let's just like start off by defining the final pressure to be PF. Alright, and we know that this like gas will assume like ideal gas behavior. So if you have like P final times V, which is like our combined volume, we know that it's equals like our N total, so it's like the total number of moles of gas in X and Y, times our R times our T. And we know that N total is, like I said, Nx plus Ny times RT. And if you simplify this, it's just Nx RT plus Ny RT. And we know that this is equals to Px Vx plus Py Vy based on the relationship that Pv equals to nRT. Alright, does this make sense to you guys so far? If it does, can you just type one in the chat if you guys understand what's going on so far? And honestly, right, if throughout the lesson, right, you don't understand something and you like want to ask me again later, feel free to just drop me a message on Discord and I'll try and answer your questions later on as well. Alright? All good? Okay. Let's move on then. So once we have this derived here, right, we know that it's Px plus Py. We know what our Px and Py is, and we know what our Vx and Vy is. So we can just find out that our Pf times 15, since like our combined volume is 15, we have 10 dm cubed and 5 dm cubed, so we have 15, equals to like 8 times 5 plus 2 times 10. So our Pf equals to 60. You guys can calculate out so yeah, Pf equals to 60 over 15, which equals to 4.008 here. Now I did something here, right, that you can't do for every question on ideal gas. Do you guys want to like try and figure out what that was? Like there's something I did in this working that involves units that I can't do for every question. Like if you guys know the answer, you can just type it in the chat. Like what do you guys think I did here that doesn't always work? I'll give you guys 15 seconds to think about it. If not, I'll just move on. Yeah? Let's think about like what I did here that I can't apply to every ideal gas question. Okay, let's answer that. So if you notice here, right, what I'm doing here is that I'm basically just directly using the volume in dm cube and the pressure in atm. But if you were to look at this equation again, right, we know that by convention, your volume is supposed to be in terms of like meter cube and your pressure is supposed to be in terms of like pascals. So the reason why this works here, right, is because we're expressing sort of like quantities in terms of these two things only. Like we're finding sort of the ratio between this and like these two things. And because of that, the units doesn't matter that much, because it's not the absolute value that we're finding here, if that makes sense. But in most questions, right, you have to convert the value that they give you to pascals and meters cubed first. One more thing, right, 1 dm cube. Okay, so it's like 1000 dm cube equals to 1 meter cube, just to make it clear. And 1 dm cube equals to 1 liter. Because these are like the most common types of units that they give you guys for like gas questions. So if that's clear, right, we'll just move on. Actually, there's another way of solving this question too, which involves partial pressures. So you can just let like the partial pressures of x and y be px and py because they don't react and mix. I mean, they don't react. So like you can try doing this question using the partial pressures method. And if you can solve it, you can just send me a picture of your answer and I'll look through it. So yeah, does everyone understand this? Because this is a very fundamental concept. Like if you understand this as type 1, and if you don't, you can just PM me in private as well. Alright, let's move on. Change this. Okay, me too. So yeah, then vapor pressure is quite simple. I'm not gonna spend too much time on this, but basically, right, the vapor pressure is like the pressure exerted by a gas on a liquid surface and the walls of the container, and your saturated vapor pressure is basically based on equilibrium. So like, actually, can I just try click on this? That's just like there's no way to. But anyway, so yeah. Basically for vapors, right, the stronger your intermolecular forces within the liquid, the lower the volatility and the saturated vapor pressure, and the higher the boiling point. Now, the reason why that happens, right, okay, let's just quickly go back to this whiteboard, is because of something known as like equilibriums. So if I declare the once again, we know that when we have something like this, let's say we say a liquid right here, like, I don't know, just like water or something, we know that the water molecules cancel, like some water molecules, right, will hit against the surface, the moving hand will hit against this, and it will just have just enough energy to break out of like the system here and become a gas. So like they just turn into a gas, and now it's floating around here. And this is like the rate at which this happens, right? And the amount of amount of water in each of these states is governed by equilibrium of liquid to gas. And what this means, right? And basically what happens is that you have a saturated vapor pressure and the rate of like both of these processes happen, like your gas going back into water and the water turning back into gas, happen at the equal rate, so the net change is zero in the system. Now that's like an equilibrium concept which we'll be going through later, but basically your amount of like gas molecules and liquid molecules don't change. Like the net effect, like there's no net change, and that's the saturated vapor pressure. And this also explains why your stronger IMF leads to a lower vapor pressure. If you have a stronger IMF right within the liquid state, there's going to be fewer molecules going to the gas state, so your equilibrium will be shifted more towards the liquid side of things, which results in a lower saturated vapor pressure and hence a higher boiling point. Like if you want to know, right, like the way boiling point works is like, let's say if it was like water on the stove, right, like your boiling point actually isn't determined by temperature in essence, it's when like the pressure within like your system is the same as your outside pressure. So if you have like trying to boil water, right, the pressure of your water has to be the same as your atmospheric pressure basically. That's when water boils. It's something really cool, but you guys can like do more research on yourself. But yeah, pressure is governed by, I mean your boiling point is governed more by pressure than temperature. It also explains like why your water boils at lower temperature in like on like Mount Everest. Because the pressure is lower, like the higher you go, because the atmosphere is thinner. So that causes your water to like boil at lower temperature because less like heat is needed to achieve the same pressure. So yeah, that's a cool fun fact. It's actually kind of useful. Anyway, let's go back to this. Alright. So yeah, and let's go to chemical energetics once. So these are the fundamentals. So whenever we do like any questions in chemical energetics, right, you should be thinking about this. Like what type of reaction is this? How can I apply the various formulae for like delta H and like Hess's law? And is this an endothermic or exothermic reaction? And what is the appropriate diagram to represent changes in the energy of the system? Like can I use an energy cycle for Hess's law? Should I use a Born-Haber process and stuff like that? So like some of the types of chem energetics one questions are basically like calculating the enthalpy change for a reaction. That's like basically the most common thing. Drawing an energy cycle and making use of Hess's law. Drawing a Born-Haber diagram and the experimental determination of the enthalpy of a reaction. I won't be going through the last point too much because it's mostly memorization and like thinking about what factors like can affect like the rate of heat loss and stuff. But anyway, let's talk about endothermic and exothermic. Now this can get very confusing for some people, so I'll just go through this part slowly. So an endothermic basic reaction is basically saying that your delta H is positive. So your starting point of the system is at a lower energy level than your final point of the system. While on the other hand, exothermic reaction says that delta H is negative, so your starting point within the system is higher than your final point within the system. And we know that bond breaking is endothermic, while bond forming is exothermic. Now the way I remember this is that I know that when a bond is formed, right, the product is more stable because we know that things react because they want to become more stable, like most of the time. Or like, okay, eventually the final like thing is the same, like everything wants to become more stable. So when the bond is formed, right, the product is like likely to be more stable. In order for it to be more stable, we know it has to be at a lower energy level. So in order for it to be a lower energy level than when it started, the bond formation has to be exothermic. It has to release energy so that the system decreases in energy. Alright? Yeah. So there's a ton of different definitions of enthalpy change, and obviously given that this is a crash course, I won't be able to go through every definition, but my biggest advice to you guys is that use a template. Like for example over here I have this like the most generic template you can use, and use this to help you memorize for like the different definitions, because like templates are the best way to memorize things, because like you want something that's flexible to allow you to like change it for the given scenario, but you also want something that's easy to memorize and does most of the work for you. So what's good for that? A template. So yeah, you guys can, I guess, buy notes or something. But yeah, if one more thing, if you guys need notes but can't afford to like get them or whatever, you can just send me a message and I'll send you the PDF copy for free. Yeah. So just things to keep in mind for different delta H values. So is it like per mole by definition? Like different definitions have different expectations for stuff. Is it dependent on a specific reaction, or is it something that's generalized? To look at the enthalpy change of formation, right, you can apply it to like anything. Like as long as you have a delta H. Wait, not say. Oh yeah, so basically as long as you have like your delta H of formation of your products and like reactants, so you can find the delta H. How do you say formation? Okay, basically enthalpy change of reaction, right, is very general. So what I mean by that is that as long as you have the delta H of formation of your products and of your reactants, you can find out whatever your like your delta H you're trying to find out. If that makes sense. But on the other hand, like for stuff like enthalpy change of neutralization, right? Like the neutralization is basically dependent on your H plus reacting with your OH minus. That's like the essence of it. So like enthalpy change is dependent on like how easy it is for you to get the H plus and the OH minus and the energy released when they react together. So like most of the time the enthalpy change of neutralization is basically determined by the strength of the acid and base and how easily they can like lose their H plus and OH minus. So you guys can look through your lecture notes for all these examples and stuff, right? And then if you have any questions about any of the definitions, just feel free to like ask later in the lesson or just DM me in private later. And just ask yourself like, can the overall enthalpy change be broken down into multiple stages? Like for example, in enthalpy change of neutralization, there's a bond breaking stage and a bond forming stage. So the experimental determination is like relatively simple. So you just have your Q equals to MC delta T and delta H is negative Q for N. Just read your lecture notes for this and understand how the graph works and stuff. And if you have any questions regarding this in the second part of the lesson, feel free to ask them. And for limitations and assumptions, think about certain features of the public experiment. So for example, let's say like we have experiments like exposed to the surrounding atmosphere and environment. Obviously the first thought that comes to your mind is that okay, if I expose something to the surrounding atmosphere and I'm trying to measure the change in like enthalpy, I need to consider like the rate of heat loss in the environment. So you think about how your value for Q and stuff will be affected, or your value for delta H will be affected. And by doing that, you can sort of determine what your assumptions are. So yeah, that's all about HESS law. So like let's spend a bit more time discussing this. So we know that the enthalpy change of a reaction is a state function, so it does not depend on the path taken. So it's like similar to comparing displacement versus distance. For displacement, right, you only care about the absolute difference between the position of 2 points and not about how you get there. Hence, the distance, right, or in this case, the route taken to go from reactants to products does not matter. And this is useful for cases where you have multiple paths to the same product. Now, finding the enthalpy change of a reaction is like relatively simple. When using the enthalpy change of formation, let's say you want to find the delta HI in terms of delta HF, right? It's products minus reactants first, and when you use bond energy, right, it's reactants minus products. So just remember that like convention and don't mess it up. An energy level diagram. Be careful, like it's generally okay, and don't combine in like things that shouldn't be combined. And for things that can be combined, it should just be the same type of enthalpy sheet. For example, if you have magnesium and trying to convert to Mg2 plus, you can convert your first and second, you can combine your first and second IEs together. But if you're starting off with Mgs, right, you need to use the enthalpy change of atomization first, making the gas, and then you can combine the first and second IEs. So that's something to keep in mind. And especially for Chem Energetics 1. Do you guys want me to like finish up Chem Energetics 2 first and then go through a bunch of questions and answer your questions, or do you guys want me to do like 1 or 2 questions for Hess's law and the energy level diagram? If you want me to continue with Chem Energetics 2 type 1, and if you want me to do a few questions on Chem Energetics 1 type 2. just repeat it. If you want me to like continue with Chem Energetics 2, then you press 1, and if you want me to answer a few questions on this topic, press 2. Alright, let's go through. Okay, let's do a few questions then. So let's switch over to this whiteboard. You guys can take a short break while I write out the question here. Alright, so just take a bit of time to think about how you would find the delta H of your decomposition of calcium carbonate given the other two reactions first. Now just think about like what you would have to do, what your starting point is and what your end point is. Like don't go straight to writing out like something and you just confuse yourself. So like spend 1 minute thinking about what we're gonna do here and then I'll start answering the question. So write it down somewhere and then see if like what you thought was the same as what I'm doing. Actually, right, there's actually more two methods of doing this, but yeah, there should be some similarities between like both of our methods, even if you use a different one. So I just spend like 1 minute thinking about how we would go about doing this question. Alright, so let's begin. Now, there's two ways of doing like energetics questions in general, unless they ask you to draw energy cycle. So if they don't ask you to draw energy cycle, right, you can go about doing this in two different ways. So the first way would be to like directly just like use algebra and solve this. Now, the way this works is that we basically ignore everything else that isn't listed in this reaction, and we put all of the reactants on one side, so your CaCO3, and we put all of the products on one side, so our CO2 and CaO. So in this case, right, we're basically trying to arrange this such that we get our products and reactants on one side. So we know that we want the CO2 on the left side, so we don't have to change the first reaction, so we can just leave it as this. And because we are leaving it this, like luckily right for us, our CO2 also comes onto this side, so that's perfectly right we want it. Now for the second reaction, we know that we want CaO on this side, so we can't just leave it here, so we have to flip the equation. And if we do that, we're basically doing the CaCO2 plus H2O becomes CaO plus 2HCl. And if we do this right, we now know that CaO and CO2 are on the same side, so that we basically solved it. Now for this, the important thing here is like to take note of like how delta H changes. So for our first equation, we know that delta H doesn't change because we basically did nothing to it. But in this case, right, we flipped the reaction. So what does that mean? Now originally, let's like look at this from an energy diagram level, like to understand what goes on when we flip a reaction. So let's say, right, we started off. Let's just take a small line. So let's say we started off with CaO and 2HCl. So CaO plus 2HCl. Let's say that this is the energy state that they're in. They're here. Now, given that the delta H minus is like negative 195, right? do you think that the position of this line for our products like CaCO2 and H2O, would it be here or here? Like, do you guys think to be higher than CaO or lower than CaO in terms of the energy level? If you think it's going to be higher, just type out higher. And if you think it's going to be lower, type out lower. What do you guys think? You just type out your answer in the chat in the next 15 seconds. Do you think that the line drawn for CaCO2 and H2O for the first question, will it be higher or lower than the one for CaO and 2HCl? Okay, so basically, right, in this case, it won't be higher. You see, right? We know that the enthalpy change for this reaction, like this one in particular, right, is negative. If it's negative, right, we know that means that our final products are at a lower energy level than our previous one. So let's just like arbitrarily assign some value to this. Let's say this is like, I don't know, like 200, right? If we minus 195 from 200, let's just say this is like our enthalpy, which it is. So if minus 200 from, like if you minus 195 from this, right, then our final state is like 5. So you know to go from 200 to 5, you have to go lower. So like our energy state for like our products in this case, right, is CaCl2 plus H2O. We know that means we know that going from here to here is minus 195. Now if going from here to here is minus 195, what would be the result of wanting to go from the lower stage to the higher stage? Can you guys like try and guess? Like if I wanted to go from like our CaCl2 plus H2O to our CaO plus 2HCl, right? What do you think would be the enthalpy change for that reaction? If going down is minus 195, what should be going up? I just type out the answer in the head. What happens when you go up? You just type it out. I just spent a bit of time thinking about this, like, and if you get what it means, right, you can just type out like what the enthalpy change of the reaction for CaCO2 plus H2O should be. Think about this for like a minute. Okay, any other answers? Alright, good, yep, it's plus 195. That's very good, you guys understand what this means. So now we know that this is plus 195. So basically, right, our delta H for this reaction, like, let's just start labeling this. So let's just say this is delta H1, this is delta H2. We know that our delta H for this reaction is now plus 195. Now, let's say, let me just erase this first. What the heck? Okay, delete. Oh wait, I'm doing the wrong thing. Oh my god. Okay. So now let's combine these two equations together. So if we were to like combine these two, right, we'll just get like plus CaCO2 plus 2HCl plus H2O becomes CaCO2 plus H2O plus 2HCl 2HCl plus CaO plus CO2. Now, for simplifying chemical equations, right, we know that if our product is on both sides of the equation, like if you have something on both sides of the equation, we basically cancel it out. So what goes on, right, is that we basically remove anything that's the same on both sides. So CaCO2 is on the left side, so we don't remove it. CaCl2, H2O, and 2HCl on both sides, so we just cancel them off on both sides. And that leaves us as our composite equation as CaO plus CO2, which is exactly what we tried to like figure out from the start. Like our original question was, what is this? Now, once you have this right, let's ask yourself, what's the overall enthalpy change of this reaction? We know that because we're adding these two things together, it's just delta H1 plus delta H2, which will be the same as saying negative 17 plus 195, which goes to 178 kJ per mole. Alright, is that clear to you guys? You just say that it's clear if you understand what happened, and if you don't, then say it's not clear. And don't feel free to ask questions. I mean, like that's the only way I can like really help you guys, because like for a crash course there's only so much content you can go through. There's a few things I miss out on, and those things that I miss out on might be the things you guys don't understand. So is this okay? Do you guys have to go through like the energy cycle diagram, or just move on? You can type something out. Okay, if you want me to go through that, okay. Oh wait, energy cycle, okay. Let's do that then. So I'll just use this question to like draw the energy cycle. So we, oh god, okay. Oh my gosh. Okay, let's. Alright, so let's just use the same question again, and let's draw the energy cycle for it. So I like to, like, it doesn't matter how you do it, but I like to start by writing out like the equation I'm trying to find out at the top for this case. So we basically want to find out this thing. This is what we want to find out, right? So just label this as delta H R. Alright? So this is what we're trying to find. Oh yeah, one more thing, right? You remember to include state symbols. I'm not doing it here because I'm lazy, but just include state symbols when we do any of these questions. So like, for example, in this case, CO will be S, CO2 will be G, and CO3 will be S as well. So just remember to include state symbols here and here. So next thing, one possible equation for CO3, the other equation that's possible for CO3 will be to add 2 HCl to it. So this will be our delta H1. Let's just label this simply say. We add 2 HCl. So we just write out like the things we're adding to this arrow, and to ensure that nothing goes wrong, right? We have to like account for everything. So in this case, we just write out the products of the reaction. Okay, maybe I'll just write out state symbols for this. So yeah, we know that if we do this, right, we get this as our products based on this equation. We also know that we add like 2 HCl to this side. We also get CHCl to H2O. So once again, just do 2 HCl, and you get delta H2, which is a negative 195. So this is our energy cycle basically. Now, by Hess's law, right, we basically know that, like how does this? Basically, right, there's two paths to this reaction. You can either go through this path, let me circle it in red. So this is one path to go from this state, like here, 1 to 2. But we can also make use of this path. So we can first go from here to here, that's 1, and then we take use of this to this. So we have 1, 2, and then 3. Now taking the red path and taking the blue path to get to our final products here, right? Our final thing here, like this is our final thing, it doesn't matter. So what that basically means is, right, is that our delta H1 from this energy cycle, our delta H1 equals to delta HR plus delta H2. Because going from here to 1 is delta H1, going from here to here is delta HR plus delta H2. Does that make sense to you guys? Like, does it make sense? You can just type out 1 if it makes sense, or 2 if you didn't understand. Like, just type out 1 if this makes sense, and 2 if you didn't understand. Or what about heart-shaped box? Do you get it? Nice. Let's move on then. And let's go here. So back to this. So yeah, this has this law. This is used for cases. And the finally enthalpy change of reaction. This thing is quite basic. It's in your lecture notes. Just follow this and understand what goes on. If you don't understand, ask me questions either. Energy level diagram. Do you guys want me to like just draw one for like MgCO2 or something? Or like NaCl? Or do you guys want me to move on to like chem energetics too and spend more time answering your questions? guys can just let me know. Like I can either throw a sample energy level diagram, or I can move on to chem energetics too. So like Gibbs energy and stuff. What do you guys want? Anyone? No comment? So I'll just move on, I guess. I'm assuming no one wants that. Okay, I'll move on then. Alright, let's go into chem energetics 2. So chem energetics 2 is very basic. Like the overall concepts in these topics, right, are quite simple. It's about how you apply them that matters. And for how you apply them, right, you need exposure to questions and practices. And that's why I want to make this lesson more question focused after this. So anyway, right, entropy is the amount of disorder in the system, and it's denoted by S. Your entropy in the solid state versus liquid state, and your gaseous state, just need to know about those. Like, of course, gases have the most entropy because they occupy the largest volume and they move around the quickest. So there's the most amount of disorder. And the entropy of the system is affected by a change in temperature, change in phase, change in number of particles, and mixing of particles. So there's different cases for all of those. You can do trivial electrons. You can just think of those examples ahead. So if we mix particles, for example, right? Let me show you guys how you can think about this. I feel like it's very important for you guys to get the chemical intuition for things and stuff. Let's just change windows to. Actually, if someone doesn't mind, right? You guys can also offer your own explanation for why mixing increases entropy if you want to. I think Anyway, that's. Oh my gosh. Okay. Let's begin. So let's say we have this rectangle over here, alright? And let's say we have a barrier between these two boxes over here, alright? So I have a bunch of gas particles moving here. Let's say 1, 2, 3, 4, 5, 6, 7, okay. And I have another bunch of gas particles moving here, alright? Now because these are two isolated systems, you can just say that the S of this is S1 and the entropy of this is S2. Alright. Now, we also know the system of this is V1 and this is V2. Now, fundamentally, right, entropy is basically the amount of disorder in the system. And the amount of disorder depends on the number of states that each system can take. So let's say there's 6 particles in this box, right? But there's 100 ways to arrange those particles. Then you have 6 particles that can take up in 100 spaces. Let's say it's the same thing for this case. Over here we have 8 particles. Let's just pretend there's 8 particles. Let's just draw 2 more. So we have 8 particles. And let's say that box is bigger, so there's 200 spaces. Now if we were to combine these two together, right, we basically will have 14 particles, V1 plus V2. We will basically have 14 particles in 300 spaces. Now logically speaking, right, do you guys think based on permutations and combinations, which of these 3 cases, right, do you think will have the most number of arrangements? Will it be in V1, V2, or the combined scenario? You can just type it out. In which of these cases can you arrange things in the greatest number of ways? I think about you're putting 14 balls into 300 boxes versus 6 balls in 100 boxes and 8 balls in 200 boxes. So which of these 3 scenarios, right, can you arrange the number of balls in the greatest number of ways? V1, V2, or the combined situation? You guys answer. Feel it's okay if you get it wrong. Just answer it. So that way I know that you guys can keep up and stuff. So do you think that there'll be the greatest number of possible arrangements in V1, in V2, or the combined situation V1 plus V2? You can just type it out. Which one do you guys think it is? If not, I'll just explain myself. Anyone? Okay, let's move on. So basically what this means, basically, right, in V1 plus V2, since you have 14 particles in 300 spaces, you can arrange the number of particles in those spaces in the greatest number of ways. So there's the highest possible number of different arrangements. Which basically means that, oh yeah, you can leave now, that's fine. It basically means that you can arrange like there's the highest number of states occupied by the particles. And because these particles can occupy more states, right, there's a greatest amount of disorder in this case. So there's more disorder because you can occupy more states. And because of that, the combined system has the highest amount of entropy. Can you guys follow the explanation? Or should I explain again? 1 if you understood that, and 2 if you need me to explain again. Like someone just quickly type out 1 or 2. Anyone? If not, just like go on first, and you guys can ask me to come back to this later. So moving on, gives free energy. So like it basically tells us that it basically tells us about whether or not a reaction is spontaneous, and tells us about the position of the system with respect to the equilibrium. So there's like 4 scenarios which we can analyze. So do you guys need me to go through that? Like the 4 different scenarios for delta G. Anyone? If not, that's pretty much it. Like for this crash course. So like for now, right, until 12, I'll just be answering any questions you guys have. So feel free to speak up now and we'll go through a bunch of questions together. So like if there's anything like that you guys don't understand conceptually in this topic, you can just ask now. Anyone?